Well, shall we start then? Yeah, okay, so welcome to the Oxford-Bristol Set Theory Seminar, and today's talk will be recorded and posted on our YouTube channel. If you look for it there, links from the webpage. So it's my pleasure to introduce Sandra Müller from the Technical University of Vienna and also at the University of Vienna. And she's going to be speaking today on the strength of determinacy when all sets are universally Baire. So thank you very much, Sandra, and you could please go ahead.
Yeah, thank you, Joe. So let me start by sharing the screen. Should be there. Okay. I think now you should have the slides. Does it work?
I think so.
Great. Okay. So yes, as you said, I want to talk about the strength of determinacy when all sets are universally Baire. But before we go into this, I want to give you a bit more of background on the connection between determinacy and inner models with large cardinals. So we start with the usual games of length omega, and the large cardinals we will look at that level will be some Woodin cardinals, and actually for our talk, finitely many. And then the next section will be on generalizations of this, and we look at longer games and games on reals. So here, the large cardinals we get is something, let me just say more Woodin cardinals, yeah? So it will be countably infinite. And then finally, I want to talk about the main result of today's talk, but the strength of determinacy when all sets are universally Baire, and the large cardinals you can expect here is a cardinal lambda that is a limit of Woodins and a limit of strong cardinals at the same time. But I will say more about this as soon as we get there. So this is the plan. And I start from scratch and just to recall what games in set theory are and what kind of games we want to look at. And please, I mean, if there are questions, just interrupt me. And there's a reason why most of the slides are empty to start with, because this gives me the freedom to fill in whatever you want to know. Okay, so please actually use this. But the first thing I have to draw, I think, is mandatory. So what kind of games do we look at? Our games have two players, player 1 and player 2, and they alternate playing natural numbers. So let's call them n0, n1, n2, n3, and so forth. So these are natural numbers, so elements of omega, and we produce a sequence of length omega. And now we want to decide who of the two players is winning. And so we want to define that player 1 wins the game, if and only if, but now we have to fill something in. Well, before we start playing the game, we need to decide what the winning conditions are. And the winning conditions are given by some set of sequences of natural numbers. And for now, I will just identify this versus the reals. And a real, I actually mean a sequence of natural numbers. And we say that player 1 wins the game if and only if the sequence we produce, so this n0, n1, and so forth, ends up being in the set A. And otherwise, player 2 wins. So we can look at this game for various sets A, and we can check in a concrete one when one of the two players is winning. What's even more interesting is if one of the two players has a winning strategy. So we say some function sigma is a winning strategy for, say, player 1, if and only if he wins the following runs. So what is this function sigma supposed to do? We again have player 1 and player 2, and sigma tells player 1 what to do. So at the beginning, we just look at sigma of the empty set. And this gives us some natural number player 1 has to do. So if we look at the definition here, this has to be a function that goes into omega because we want to have natural numbers. And then player 2 plays some natural number n1. And now player 1 again plays according to sigma. So he just plugs in whatever we have done so far. It doesn't really matter if we plug in the own moves or not. Let's just do it like this. So let's say we ask our function. So this is the status of the game we are at the moment. We have played sigma of the empty set and player 2 has given us n0. What do we do next? And the function gives us some other natural number, and this is what we are playing. And we continue. So this is a function that takes finite sequences of natural numbers, and whatever player 2 does, it tells us what to do next. And if we follow what sigma tells us, then we are going to win in the end. So this produces the sequence in A. And this is all we need to define the most central concepts of this talk, and I guess about everything I'm doing in my research. So we say the game is determined if and only if one of the two players has a winning strategy. So this game, let me call it G of A, or just the set A is determined if and only if one of the players has a winning strategy. And we can define winning strategies for player 2 just analogous to the ones we just defined for player 1. And we can ask, of course, which sets are determined, and we can just like formulate this as an axiom and just postulate that all sets are determined. And this is what's called the axiom of determinacy. So what does this say? It just says that all sets of rails are determined. So the nice thing about determinacy is that it's a concept that I can define on one slide, and that you can actually just tell a first-year math student, or even lower. Yeah, I mean, there's really not much behind. I mean, okay, in this case, the games are infinite, but as logicians, we are used to that. And the rest is really standard. The interesting thing about determinacy is that if you ask this question, what sets of rails are determined, the answers are highly non-trivial. And before I go into that, let me just summarize on one slide what determinacy is good for. Just as a motivation to look at these things. And determinacy is a concept that has been studied since the 50s. And one of the most influential results, I think, is the first theorem on the slide. So has shown that if all sets of rails are determined, then all sets of rails are Lebesgue measurable, have the Baire property, and have the perfect set property. So determinacy is something that takes the chaos and puts it into order. And because there are no pathological sets of rails, everything is very nice structure. It's Lebesgue measurable, Baire property, perfect set property, and so forth. And there are other results along these lines. And there are many results of consequences of determinacy, and I just put a second one that's more recent to show that there are also the cases of determinacy that are current and nowadays research that are still very interesting. So this result was produced 2 years ago with Raphael Carra and Andrea Medini at Vienna. And we proved that if all sets of rails are determined and X is a zero-dimensional homogeneous space that is not locally compact, then X is strongly homogeneous. So this is something that you can ask in general topology. And surprisingly, the answer I mean, it's not surprisingly because there's a counterexample under the axiom of choice, so you know that you need something. But maybe surprisingly, this is actually the axiom of determinacy seems to be exactly the right thing to assume to get this nice structural property. And I mean, I'm not defining what these notions are because this is not the central point of today's talk. I mean, I can go into more details if you want, maybe after the talk, but this is just another example where you can use set theory and this determinacy concept to prove things that are completely outside of set theory. And the nice thing is even that all of these results have local versions. So for example, in case you just don't like the axiom of determinacy and you just like, I don't know, a Baire version or analytic version, the Baire version brings you back to Z of Z. And this has been known before for these kind of results. But for example, if you just ask about analytic or projective, you can just put it here. So if all, let me say projective sets of reals are determined, then all projective sets of reals are Lebesgue measurable, have the Baire property, have the perfect set property. And the same for the other results. So I'm just stating it for the whole axiom of determinacy because it's nicer to formulate and it's more general, but the proofs are all very local. So now that we're already speaking about local determinacy, let's look at this a bit more, because local determinacy is something that if we're very local, we can prove in Z of Z, and sometimes we need to go beyond. So the very first result about the consistency of the determinacy statement was by Gale and Stewart already in the paper where they defined these two-player games. And they proved that every open and every closed set is determined. And then in order of consistency strength, the next canonical object is the Baire sites, and Martin proved that they are determined in Z of Z. And then Martin also showed that analytic sets are determined, but here the picture changes because to prove the determinacy of every analytic set, he needed something that's called a measurable cardinal. And Martin C proved that sigma 1n plus 1 sets are determined, but they also needed something beyond Z of Z. They needed n Woodin cardinals, an additional measurable cardinal. And the last thing is just like the 0 = 1 hypothesis. So assuming the axiom of choice in Z of Z, there is a non-determined set. Yeah, so if we want to climb the whole hierarchy, ultimately we reach a contradiction leads to the axiom of choice. And if we look at these statements, the very first and most natural question that arises is whether these large cardinals are actually necessary for the determinacy of these sets of reals. Yeah, maybe the people who proved the theorems were just not thinking hard enough. Yeah, maybe this was just a coincidence that they used this, but maybe they didn't really need it. And this has happened in the past, by the way. Some of these results were proven for much stronger large cardinals that they are known to be consistent from nowadays. But the answer to this question is in some sense, yeah, so we actually need them. And I want to make precise the next slides what I mean by that. And tightly related to this question is the question, how can these large cardinals actually affect what happens with the sets of reals? If we think about this again and just look at the set theoretic universe V, and here are the ordinals, then the large cardinals are somewhere here. Yeah, this is, for example, a measurable cardinal, a Woodin cardinal, or whatever you want. And determinacy is a question about sets of reals. So this is somewhere here. Yeah, the power set of the reals. And this is strange, yeah, because we have this large cardinals, and we have the power set of the reals that sits so far at the bottom. And how can there be an interaction, right? If you look at this, it looks like the theorems cannot be optimal. And the way I stated them, they are not optimal actually. And the reason is what we have here in the corner. So the answer is in some sense that they don't, but their countable sisters do, yeah. Because what we will get is we will look at countable models, and these countable models are called mice. This is why there's a mouse sitting here. And these mice, they have large cardinals, And they are actually the object that affects what happens with the sets of reals and the determinacy. So what we want to look at is mice with large cardinals. Yeah, and this is really going to be equivalent to these determinacies. Okay, so let me just briefly mention a couple of results that are known in this area to give you a feeling about what can be done. And I'm not going to define these mice formally, but I'm going to draw a lot of pictures. So the first result in this area was the equivalence for analytic determinacy. Harrington and Martin showed that it's equivalent to analytic determinacy that X sharp exists for all reals X. So X sharp is one of these countable mice, and it looks as follows. We start with X and we build something like L of X, the constructible hierarchy, but now in addition, we have some kind of top measure. This is what we call the sharp of the model. And this model has other nice properties, but the idea is that this is just the countable version for our measurable cardinal. Yeah, I mean, this top measure is something like a measurable cardinal. It's not a measurable cardinal in the model, strictly speaking, but it's some kind of a trace of a measure. And this is how we code this into a countable model in some sense, yeah. And this countable object is what's actually equivalent to the determinacy. And we can do similar things for the other statements that I had on the chronological order slide. So for example, for projective determinacy, or here sigma 1n plus 1 determinacy, we also get a mouse. Again, the mouse starts with some x, and it has our top measure, the sharp. But now we need more large kernels in the model, and we actually add n Woodin kernels. So this is what's denoted by mn sharp of x. It's a canonical model that has this iterability property, and I mean, as I said, I'm not making precise what this means, but it's just a nice property, and the model looks exactly like what I draw here. We start with x, and we again build something like L of x, but we in addition can add these large cardinals here. And so this is also an equivalence, and proving this took much longer than the result for analytic determinacy, and the proof is also much harder. And it's like, I mean, one of the implications is like 120 pages, and the other one is another 50 pages or something like that in written paper to just prove this theorem. So the things are getting very complex if we climb up the hierarchy. But we can do even more, and we can look at more general games. Yeah, I mean, what we want to do is we want to characterize determinacy in terms of large cardinals and the other way around. And so we need to look for other determinist statements than the ones we already have. And one way of generalizing is by looking at longer games. So we again have two-player games, player 1 and player 2, and they again play our natural numbers in 0 and 1, and so forth. But no one stops us playing to play longer than omega. Yeah, I mean, after omega many rounds, we can just continue, and player 1 can play a natural number n omega, and player 2 can play n omega plus 1, and so forth. And we can continue that for as many rounds as we want. And let's just say here, we do this for alpha, say steps, because rounds sounds like more a game of length omega. So we can alternate alpha many times, and just again can say that player 1 wins if and only if the sequence we produce, and now this is a sequence of length alpha, is an A, if we start with a set A of natural numbers, of sequences of natural numbers of length alpha. And if we do that, we can again find a connection to large cardinals, or to large cardinals. And I mean, here are some examples of the results that we can prove. For example, if we assume that games of length omega times omega plus n, so this means that we have omega plus n many of these rounds of length omega, and an analytic payoff condition, then there's a mouse with omega plus n Woodin cardinals. So, and I mean, if we want to, we can just build it over X. So we first have omega Woodins, and then we can put n more Woodins on top, for example. And Namchuang showed that if we take an indecomposable ordinal of the form omega to the alpha, and we look at determinacy for games with omega to the alpha many steps, then there's a framework with omega to the alpha Woodin cardinals. And we can actually combine these two results. And if we have a game with omega times omega to the alpha plus n many rounds, there's a framework with omega to the alpha plus n Woodin cardinals. And if you play this a little bit further, I mean, I didn't check all the details, but I strongly believe that these methods give you equivalences for all countable ordinals alpha. Yeah, by just combining these techniques behind the theorems on this slide. So this tells us, okay, I mean, it makes sense to look at longer games. This gives us more Woodin cardinals, but it doesn't really bring us out of the area of a number of Woodin cardinals. Yeah, this helps us understanding numbers of Woodin cardinals, but that's it. So let's try something else. Another way we can generalize our game is we can, instead of playing games of natural numbers, we can play games on reals. So again, we have two players, and now we don't play natural numbers, we play reals, so x0, x1, x2, x3, and so forth. So, I mean, as I said, my reals are always sequences of natural numbers. So let's be honest and write sequences of natural numbers here. And again, we can fix some set A that is a sequence of reals. And we can say player one wins this game if and only if the sequence reproduced is in this set A. And we can define winning strategies and so forth. And we can ask, okay, how strong is determinacy for these kind of games? And actually, we can understand at least roughly how strong this is. And I showed with Juan Aguilera that projective determinacy for these kind of games is equivalent to the existence of M sharp of R. So what is this? It's another mouse, and it looks very similar to the ones we already had. So we have this sharp, our top measure. And we have n Woodin cardinals. This is exactly as before. The difference is that now we don't start constructing with just a single real X. We put all the reals in the bottom. So this is stronger than what we had before. Before we were just putting one real X here, and then the rest. But now we allow all the reals. So this is no longer a countable model, for example, but it's like almost countable. Yeah? It's countable despite from the fact that we started with all the reals in some sense. Yeah. But again, okay, I mean, this gives us a result, and it's nice to understand how these games look like, but we're still somewhere in the area of a number of Woodin cardinals. Yeah. So what else can we do? I mean, one way is to look at longer games at this point. And that's also something that's not very well understood. But there's a different approach to strengthen the determinacy hypothesis. So what else can we do? Another approach is to keep playing games of length omega. So forget about the generalizations of longer games, but impose additional structural properties on the model. Yeah, so it's like in the picture, we're still playing chess, but if we are mice, then the cat in the background is really frightening us. Yeah? And we need to get stronger to survive. So this is roughly the idea. So what are the examples? One example we can look at is we can impose that sets have to be Suslin. So being Suslin is a generalization of being analytic. We say a set of reals is Suslin if it's the projection of a tree on omega times kappa for some ordinal kappa. So being analytic just means to be the projection of a tree on omega times omega. So our set A here is the projection of some tree T, and T is the tree on omega times kappa, if we think about Suslinness. And under the axiom of choice, this is actually a very boring hypothesis because it's a very easy exercise to prove that every set of reals is Suslin under AC for a tree on omega times the continuum. But under the axiom of determinacy, this becomes really interesting. So if we work in models of ZF, or ZF plus AD, then there are natural models in which not every set of reals is Suslin. For example, L of R. If L of R satisfies AD, this is not a model of all sets of reals are Suslin because this is going to be stronger. And to give you a feeling about how strong this is, I put the following theorem on the slide. So Martin and Woodin showed in the 80s that under AD, the statement that all sets of reals are Suslin is actually equivalent to ADR. And ADR is determinacy for all games on reals. So games of length omega, just like the ones I had on the previous slide, where the two players play reals instead of natural numbers. So this is much stronger than just plain determinacy. And this leaves us with the question of how can we connect this with large cardinals? What is the right large cardinal hypothesis to look at if we want to look at the statement AD plus all sets of reals are Suslin? Yeah, so now the all sets of reals are Suslin are the cat in the background. Yeah, that makes it harder to get the determinacy. And Woodin proved one direction already in the 1980s with his famous, the variant of his famous derived model construction. So he showed that suppose there's a cardinal lambda that is a limit of Woodin cardinals and limit of less than lambda strong cardinals, then there is a model of AD plus all sets of reals as Suslin. Okay, so let me draw a picture. How does this look like? We have a model and it has some cardinal lambda, and this lambda is a limit of Woodin cardinals. So we have these Woodin cardinals here, and at the same time it's a limit of less than lambda strong cardinals. So let me draw them here. So these are the less than the strong cardinals. So how do they look like? If you've seen these pictures with extenders before, then this is how it looks like. So the way you can think about this is, for example, so this is a strong cardinal all the way up to lambda, which means that there are elementary embeddings that are pushing this cardinal here to above any ordinal you fix below lambda. So we have very strong elementary embeddings because these elementary embeddings can push this point as high as we want, but below lambda. This is by less than lambda strong. So this is what a strong cardinal is, or less than lambda strong cardinal. And the thing to keep in mind in this pattern here is that what we have is we have plenty of Woodin cardinals that have these overlaps. Yeah, so there's one extender or one elementary embedding that is pushing the critical point somewhere here, and there's another one that's pushing the critical point here. And if you think about it for a moment, you can see that if you have these kind of patterns, they generate many more large cardinals. For example, they generate more limits of Woodin cardinals that are sitting here, and you can really push these points very high up and so forth. So this adds a lot of complexity. This is much more than just having a limit of Woodin cardinals. Yeah. So just having these blue ones is very, very weak compared to having this combined pattern. And this combined pattern suffices to get a model of AD plus all sets of reals S. And this is what Woodin proved. And Steele showed in 2008 that this is optimal. So for this background hypothesis, this is exactly what we need in terms of large cardinals. Okay, so we can look at a further strengthening. Universally Baire sets. Being universally Baire is even stronger than being cislen because it means that you're the projection of a very nice tree. So let me just write this maybe. So it's the projections of nice trees. So what are nice trees? For a pair S and T of trees on omega times kappa, and any set Z, we say that ST is Z absolutely complementing, if and only if the projection of S is the complement of the projection of T, but not only in V, but in every col omega Z generic extension. So there are two things we need to prove here. So this includes that the projection of S and the projection of T is disjoint in every generic extension, and that the projection of S and the projection of T is still fat, so it still unions up to all the reals in every generic extension. And this first condition is actually very easy. This is just absoluteness. The second one is the hard one. So ensuring that these two trees are still fat enough that their union gives all the reals in every generic extension is really where the content lies in this definition. Okay, and if we have such trees, then we say a set of reals is universally Baire. So a set of reals is universally Baire if for every set Z, there are Z absolutely complementing trees, S and T, such that the projection of S in V is the set A we want to characterize. So A is the projection of a tree, but of a very nice tree because it's complemented, absolutely complemented by another one. And this is a very strong notion because not even under the axiom of choice this is true for all sets. So under the axiom of choice, there are sets of reals that are not universally Baire, because every universally Baire set has regularity properties like Lebesgue measurability, for example, and perfect set property and these kind of things. These are consequences of universally Baireness, so they cannot hold for every set in Z of Z. But we can ask whether this holds in a model of determinacy, because there all our sets have the regularity properties. So how strong is this? How strong is it to impose that AD holds plus all sets of reals are universally Baire? Paul Larson with Grigor, Sargsyan, and Wilson showed a couple of years ago that if there is a cardinal lambda that is the limit of Woodin cardinals and the limit of fully strong cardinals, then there is a model of AD plus all sets of reals are universally Baire. And Grigor conjectured that this is optimal, but they were not able to prove that at this time. So how does this model look like? We have a similar picture as before. We have a cardinal lambda. This is the limit of Woodin cardinals. And it's also the limit of these strong cardinals. And I mean, first of all, they're all strong up to lambda. So this is the picture I had before. The difference now is that they're also strong past lambda. Yeah, so each of these cardinals, they go all the way up. Yeah, even outside the slide, all the way up to the ordinals. They're fully strong. They're really fully strong. So we can push each critical point here, or each cardinal, as high as we want, in particular across lambda. And this is what gives the extra strength in this result compared to Woodin's had before. And so as I said, it was conjectured that this is optimal. And the good news is that this conjecture holds. So we can prove a converse. Suppose there's a model of AD plus all sets of reals are universally Baire. Then there's a model of Z of Z that has this cardinal lambda that is a limit of Woodin cardinals, and at the same time a limit of fully strong cardinals. So we can go the other way around. We can construct such a model. And in the rest of this talk, I want to give you some hints on the proof of this result. And yeah, so maybe I should say already, in case you, of course, in case you have questions, please ask. And in case you want to look at this, I will probably upload a preprint of this tomorrow on my webpage. So I have it ready here. I just didn't find the time to upload it yet. And or I can just email it to you if you want. Just post me an email and then I can send it to you. So what are the ideas behind this result? Before I go into the proof of this particular result, we need to look at inner model theory, descriptive inner model theory, a little bit more. Well, I've discussed the connection between determinacy and inner models in the first half of today's talk. And now this deep connection between these two components actually need the third component. And John Steele calls this the triple helix. And I like the picture very much because these three things are very intertwined, and we have to keep going back and forth between these different hierarchies. And so I think the helix is a very good picture to keep in mind for these things. So what is the third component? I want to look at the third component is what we call hybrid mice. So the informal way of stating it is these are in some sense mice with superpowers, or mice that are as strong as a lion. Yeah, this is what the picture is supposed to tell you. Yeah. So it is a mouse. Yeah. You can see, this is a mouse as well, but the strength it has is much stronger than what you would expect from a mouse. And what we should discuss is what is the strength there? What are the superpowers? And in this case, the superpower is given by iteration strategies. So let me draw a picture. So hybrid mice go back to Grigor Sargsyan, and actually ultimately they go back to Woodin, but Grigor formulated them formally. So what is the picture? We have some universe, and the hybrid mice we want to look at, they have Woodin cardinals, delta 0, delta 1, delta 2, and so forth. So these are Woodin cardinals. So at the moment, this could be, for example, this model M and sharp I defined at the beginning. Yeah, we start constructing and we add finitely many Woodin cardinals, or even infinitely many Woodin cardinals if you want to. But now we need to think about strength. And the strength here comes from the fact that here we add more than just the Woodin cardinal, and we also look at an iteration strategy. So sigma 0 is an iteration strategy for the model up to delta 0, and we feed this in the hierarchy. So the model knows in some sense how to iterate itself, or how to iterate its initial segments, and this gives a lot of extra strengths. And here we have the strategy for the model up to delta 1, and we feed this in at the next level, and so forth. So the model looks, maybe let me start with, yeah, why not? We start with this L of x at the beginning. Yeah? What I'm writing here now is not the most formal notation, but I think it's better for your intuition. So the very first model we looked at today was this L of x. Remember, we had this x here, and there are no large cardinals at all at the beginning. And we added the sharp, but we don't need that here. Yeah? So let's just look at L of x. And then the next step was that we added Woodin cardinals, for example. We had this model, and then we had some Woodin cardinals. And these Woodin cardinals, they are witnessed by extenders in the generalization of measures. So we have this extender sequence. In the model, witnessing that we have large cardinals. And now for our hybrid mice, we add a third component to the model. I mean, we have the universe, the extender sequence, and now we also have a sequence of strategies. And I mean, formally, you need to do a lot of work to prove that you can do this in a nice, fine structural way, such that this model still has all the nice properties that L has and that we want L to have, at least the important ones. Yeah? But this is the idea. So we add these superpowers, these strategies, and I mean, there's a reason why I'm drawing the strategies in the same color as the strong cardinals before, because what we want to do is we want to find a translation between these strategies and the strong cardinals, because this is what we are really aiming for. Yeah? I mean, in the theorem, what we want to have is we want to have a model that also has these Woodin cardinals, but instead of strategies, we want that it has strong cardinals that are sitting here. And this is the translation we have to work for. So going back to this triple helix picture, we can now see the way that the proof is going, at least roughly. So here, I mean, we start with the determinacy side. So here we have a model of AD plus all sets are universally Baire. And on the mice side, we have a model with a limit of Woodins and Strongs. And what we want to prove is that these two are equivalent. And what we do is we go through these hybrid mice and we prove that we can actually go this way. So from the determinacy, we construct a hybrid mouse, and from the hybrid mouse, we construct a real ordinary mouse. And so these are two steps that we need to prove. The second one I already hinted at roughly. So this is the translation procedure. Someone wants to translate strategies into strong cardinals. And the other error here is so the keyword for this is what's called hard analysis. So what we do is we use descriptive set theory in order to construct together within a model theory such a hybrid mouse. So let me say a little bit more about what these things are. I mean, what I'm doing now is I'm giving you the proof or the ideas behind the proof like 3 times, and I'm keep digging into the more details. Yeah. So this is the general picture, and now I'm going to give you a little bit more about these arrows, but only slightly more, and then I will, in the third round, go into this, but also just with a little bit more details, and just give you some intuition of what's happening there. Okay, so first round. So some ideas behind these 2 green arrows here. Yeah? So this arrow and this arrow. What do we do? So what is the idea behind this hard analysis? The idea is we construct a direct limit model as somehow an iterate of all suitable mice in in our model of AD plus all sets IUB. Yeah, so we work in our model of AD plus all sets IUB, and we look at what mice we have. And here in our model of where all sets are universally Baire, the iteration strategies for these mice are very nice because they're universally Baire. So we know how to interpret them onto generic extensions, for example. This is exactly what universally Bareness allows us to do. So universally Bareness is a property that allows you, if you have a small strategy, you can turn it into a very big one, a very long one, because we can go to all generic extension, collapsing all kinds of things. So these small things can be enlarged. And this is why universally Bareness is a useful property here. And this is where this is used. And in some sense, we just collect all the information we have. And we look at all suitable hybrid mice and we compare them all. And we just build one big model where everything is in. Yeah, we just collect all the information the model has and put it all into one hybrid mouse. So this direct limit model here is our hybrid mouse, and we take it, and now so we start from this hybrid mouse, and we want to translate its strategies into strong cardinals while keeping the Woodin cardinals. Yeah? It doesn't help if we lose the Woodin cardinals because we need them as well in our final model. Yeah? Remember, this is how the final model is supposed to look like. We have some limit lambda of Woodins and also strong cardinals. Yeah? So these are the strong cardinals. So we need both. Okay, let me formulate the translation procedure a little bit more. So this is the main technical new thing in this result. And this is also something that I believe can apply to other constructions as well. So this is why I'm formulating this in more general terms. And translation procedures have been introduced by Steele, and they have been extended by Zhu and Sargsyan. And this is, so I mean, Sargsyan has a slightly different attempt to translation procedures, and this one is extending Sargsyan's one. So we start with some nice hybrid mouse, and this translation procedure results in some ordinary mouse with a cardinal lambda that is a limit of Woodin cardinals and limit of fully strong cardinals. So let me just draw the picture again. So we have the Woodins here, and we start with the model where we have strategies, sigma 0, sigma 1, and so forth. And what we do is we keep the same Woodin cardinals. So they just don't change at all. But instead of the strategies, we have these strong cardinals that are strong all the way throughout the ordinals. And a nice additional feature of our model is that all hulls are triple. And so if you know some inner model theory, you've probably heard that iterability is a nice feature you want to have. And the other translation procedures don't yield iterable mice. I mean, they construct inner models with large cardinals, but these models are not iterable. And I mean, the reason why I was aiming for an iterable model is because I couldn't finish the proof without knowing that the model is iterable. So I had to prove iterability, and then I succeeded. So in this case, this is, I mean, this is a nice additional feature that is crucially used in the proof. But I believe it's nice because if you want to apply these techniques to other situations, iterability is really something that helps you use the model you get, because you can compare it to other models, of course. It's really one of the key, or the key feature inner models can have. Yeah, so this is kind of nice about this procedure, I think. So how does the translation procedure look like? What is the idea? let's see. How do we do this? So we want to construct the model from bottom up. And there are some rules we follow. So whenever there is an extender in the background model, that we can add to our model M, this mask construction, then we do that. And this is giving us the Woodin cardinals. Because the Woodin cardinals were witnessed in the background models, and what we do is we just take these witnesses and we add them to our model as well. So this gives us a model that looks like this with these Woodin cardinals. So, I mean, there's an argument behind this, and this is what's called fully backgrounded constructions, and they go back to Mitchell and Steele from somewhere in the 80s. But this is known how to be done to inherit the Woodin cardinals. Okay, so the more interesting part is how do we get the strong cardinals? So we start with something that let's say, I mean, we start by taking all the information we already have. So for example, there's some cardinal kappa 0 that is strong up to delta 1. So that's less than delta 1 strong. And also there's some kappa 1 that's less than delta 2 strong. And so forth. This just comes from the fact that the delta i's are Woodin cardinals. Being a Woodin cardinal means being a limit of strong cardinals up to this delta. So this is automatic. So let kappa I be the least less than delta I plus 1 strong cardinal in our model. Okay, so this is easy. But now what we need to do is we need to add extra extenders. For example, we need to add an extender like this. So we add an extra extender E, or extra extenders to witness strongness. But now we have to be careful, because we cannot just add everything. I mean, I said I want to have a structure that's iterable in the end. And for iterability, I need to be a bit careful. I need to make sure that I only add extenders where I know how to iterate them in some sense. And this is the key property here. So we add these extra extenders, E, to witness strongness if E is generically countably complete. So this means E is countably complete in all. So let's say E has critical point kappa I, then I want that it's countably complete in all less than kappa I generic extensions of our background model. So this ensures that the only extenders we add are nice enough to get iterability, and it will actually also ensure that we get a certain characterization property that I'm not going to define, but I just want to hint at that there's a bit more behind this. I mean, this is the main reason is to get iterability, but another reason is also to get this this characterization property. And I mean, it's impossible to prove on one slide why the construction works, but there's one part of the argument that I want to show you, because I think this is very nice and gives you the idea, and maybe it at least gives you some idea why iterable models are relevant here. So let's look at our M that we constructed. And so let's say we have delta 0, kappa 0, delta 1, kappa 1, and then delta 2 somewhere here. And suppose it doesn't work. Say kappa 1 is not fully strong. So let's say kappa 1 is not psi strong. For some psi somewhere. Yeah, we know that it's less than delta 2 strong, so psi has to sit above delta 2, but there could be psi here that witnesses that kappa 1 is not fully strong. So there's no extender that's going all the way up here. Okay, so what do? We take a hull and bar. So a collapse of a hull M bar such that M up to kappa 1 is contained in M bar. So this is the same kappa 1, and the models agree up to here. And but at the same time, the size of M bar is below delta 2. And now, so this has some collapse of delta 2, and it has some collapse of our psi, some psi bar, and M bar thinks that psi bar is not fully strong. So M bar thinks that kappa 1 is not psi bar strong. Okay, so what do we do here? We compare M bar and the construction of this M, and what will happen is, so this iterates to some model M star. So this iterates to some psi star. There's some delta 2 star, but we can actually prove, and this takes a long argument that uses this characterization, but it's possible to show that actually this just iterates to an initial segment of M. So this M doesn't move, and this just becomes an initial segment. Okay, so now is the key point. Why did we do this? Well, we knew in M that kappa 1 is less than delta 2 strong. Yeah, this is how we defined it. So this has an extender F that looks like this, for example. In particular, this extender F overlaps this psi bar. So what we can do is we use this extender F to define an extender E on this model M bar. So we can define E and argue that E is on the sequence of M bar. So this is a contradiction now, because we suppose that kappa 1 is not psi bar strong in M bar, but E is witnessing that it is, because E is an extender that pushes kappa 1 past psi bar. So we use the fact that we have the small model that iterates to an initial segment below delta 2 to derive a contradiction here, and use the fact that we pick these kappa 1 less than delta 2 strong, that we get automatic from the Woodinness of delta 2. So the heart of the argument is a comparison argument, and this needs that this model is iterable. And this is why I needed to prove iterability for this construction in order to make this work. But the good thing is it works out. And let me just summarize on one slide what what we've shown, or what I at least tried to convince you of in some sense. So we have seen the deep connection between determinacy and innermost with large cardinals, and also with the third component in our triple helix with hybrid mice. These are the mice with the features of a lion. And if we use this deep connection between these three things, we obtain the following corollary. So this is the result I discussed together with the one of Larson, Sargsyan, and Wilson. The following theories are equiconsistent. ZF plus AD plus all sets of reals are universally Baire. And ZFZ plus there's a limit of Woodin cardinals, there is a limit of strong cardinals. Okay, thank you very much for your attention.
Thank you very much, Sandra. So why don't we all thank the speakers. So. Are there any questions? So I have some questions. So you talked about these sort of transfinite games longer than omega. Determinacy principles. I know it wasn't connected with the main part about universally Baire, but I find it very interesting. But I noticed that all of those games that you talked about have a fixed length, a fixed countable length. And I happen to be looking at a lot of games that have somehow variable countable length up to omega 1, but they all have the form where the players are taking turns putting information in, like, for example, there's a countable graph and they're coloring the edges. So they're building up to a total coloring, but it could take any countable ordinal length of time to get the complete coloring. Or, for example, maybe they're placing stones on a board, like in infinite hex. And the board might not be completely full at any stage, so they have to keep going, but at some countable ordinal stage, it's going to be full. And then the winning condition is maybe a very simple property of this countable object that they're creating. Maybe you could formulate all those games like they're building a reel by specifying digits, but not in order, jumping around, right? And so can you say anything about determinacy principles? If I have a property of a set of real numbers, I mean, infinite, Baire space reals, if it's very simple to define the winning condition in terms of the countable object that they're building, am I going to get determinacy for these long games or not?
So there's something known in this area, but there are also a lot of open questions. Very interesting open questions, by the way. So one thing that might be interesting for the games you're describing is a result of Itai Neyman, where you prove determinacy for so-called continuously coded games. So the length of the game is coded in a continuous way by the two players while they are playing. But so these games have a similar feature, like what you are describing. The two players start playing, but they didn't fix the length of the game at the beginning. They only know that they will stop at some countable stage. And if the coding is sufficiently nice, then these games are determined, but you need much more large cardinals for this. But it's also okay. I mean, I hope I'm not saying something wrong, but it's in the area, I think, of a strong and a limit of Woodins.
Okay.
But yeah, I mean, this is in his book. If you look at Itai's long games book, you can find it in there.
Some time ago on this, right? Or it was more than 10 years ago, right? Or
yeah. And but actually, I mean, a very interesting open question is whether this is optimal.
Oh, I see.
And this is one of the things I'm actually planning to work out in the future. I think this is, I mean, there are several questions along these lines, but there's hope that these things might be optimal, but it's not known.
I see. Okay, well, thank you very much.
Yeah, and whether actually, if you have like something written where you look at these kind of games, I would be very interested in looking at the formulations.
Right. Yeah. Are there any other questions?
Yes, I mean, I raised my hand, but
oh, I'm sorry, I missed it. I'm sorry, Philip.
That's right. It's okay. So this kind of translation procedure, I mean, is this just tailored very much to the situation that you have in hand, right? Or is it kind of scope for this to be more widely applicable?
So actually, it's not really tailored to the situation I have in hand. I think it's rather widely applicable. So let me just go back to the statement. I mean, I didn't say precisely what I mean by suitable hybrid mouse here. But the suitable hybrid mouse I need is exactly what you would expect and what you get in many situations. So it looks precisely like the one on this picture. So the only thing I need is that it's this mouse that has omega Woodin cardinals and has these strategies, and the strategies need to have a couple of nice properties, but also nothing special. I mean, all of the properties that I use have been known before.
Right.
It's not a new property.
Can I ask something? I mean,
yes.
I had another question, which was literally about the what you've got down on the bottom right is structure, sequence of extenders, sequence of strategies. So, I mean, usually we think of constructing from the extender sequence. So we think of that as L square bracket X comma E vector.
Yes.
So should I understand the sigma vector there as being just an amenable predicate to structure, or are we constructing from initial pieces of sigma?
So sigma has exactly the same role as the extender sequence.
Okay, all right. Okay, that was just one thing. Yeah.
Yeah.
So
I mean, I didn't really finish the writing there, and I left it with L of X on the left-hand side.
Yeah, that's fine. So you're thinking this is probably more. It looks like it is more widely applicable. This translation procedure. Right?
Yeah, I mean, this is one of the advantages of the procedure compared to. Let me just go back here. Compared to the one by Steele and Zhu, I mean, these ones were tied to very specific 80+ models. Yes, and this is another advantage. I think that this doesn't use any 80+ theory.
Right.
So, I mean, it's not necessary here because if you have a model of AD plus all sets of where it's a UB, you get ADR automatic. And this already gives us a lot of nice background theory in some sense to work in. And yeah, I mean, so to formulate this theorem in full, I mean, you need like, I don't know, half a page or maybe even a bit more of properties of sigma of the iteration strategies.
Right.
But as I said, I mean, all these properties have been known since Grigor's thesis and even earlier. So they're very common, and there's not a single new property of the iteration strategies that I needed to introduce. The only thing I needed to do is to prove that if we are in our model of all sets IUB, then these properties hold.
Right. And then at the punchline, are you using some initial segment condition of some kind to get that the extender is on the M-bar sequence? Or, I mean, you said there was some argument at the end to show.
Yes. Yeah, I mean, this is actually, I mean, it's a couple of arguments that come together. So I mean, first of all, the extender is just defined as the pre-image of F.
Yes.
In some sense, yeah, by this iteration embedding. So this is okay, but now we need to prove, as you said, that it's on the sequence of M-bar.
Yeah.
And for this, let me just draw the background models here as well. Right? I mean, so M was a construction in some hybrid model, and this is this W. So this is the hybrid mouse. So what we really do is we take a hull of the background model to save this information. And what we need to prove is that E, so first we need to prove that E is actually in W bar, and we need to prove that E is generically countably complete in W bar, and if it is, then it gets added to M bar by the construction. And I mean, formally, we also need to prove that E coheres the construction.
Right.
So it's allowed to be added. And so let's see. So these 2 and 3 roughly follow from the same properties for F. I mean, 2 is actually rather easy because F has this property. And the fact that this coheres the construction, so we can add it, also sort of follows from the fact that F was added here, together with some fine structural arguments. And this is actually, I mean, this looks very innocent, but this is very hard. So how do we prove that this extender is in this model W bar? Here we use that the extenders are not only given by this feature of being generically countably complete, we use that they can be given by operators. These operators go back to Steele in this very first translation procedure. And the nice thing about the operators is that the operators are definable. So what we prove here, the idea is that E is given by operators S or S of X, and this S of X is in M1 sharp sigma for this strategy sigma of X.
So it sort of condenses well.
X. Yeah, so the nice thing is that we know that it's once we have sigma and the Woodin cardinal or M1 sharp sigma in our model, we also get the operator, and then we also get the extender. Yeah, so this is somehow, this looks very innocent, but
it's not.
This needs a significant argument. The other ones are easier.
Right, and countably complete. I mean, even generically countably complete is enough. It's not some fancy kind of completeness. Is it just? Right.
Yeah, I mean, it's the same. I mean, you could also just say that it's less than kappa I complete.
Right.
I mean, the main reason why generically complete is because I want to take these hulls that contain, for example, kappa 1. So I need to be able to do this comparison and to iterate this model. So I need to have enough completeness here to iterate above kappa 1.
Right.
So I mean, if this would be a countable model, countably completeness would be enough.
Right.
But since this is a model of size delta 2 or below delta 2, we need a bit more.
Right. Thank you.
But yeah, I mean, I was actually happy when I saw that this generically countably complete condition is enough for the translation procedure, because I mean, to prove this to prove this picture in some sense, yeah, that you can iterate and that this model doesn't move and you get this is an initial segment and so forth. You also need a characterization of the extenders, because you need to argue that if you have 2 extenders, then they're going to be the same and they are not used, because otherwise the picture would look different, right, if you start iterating on the M side. And so this also needs a characterization of the extenders that we added. And luckily, it just follows from being generically countably complete. So the definition is much easier than it really is in some sense. It's a bit cheating.
Right.
But I was happy when I saw that I can do it, because for talks like this, it's very convenient to be able to define the procedure without like 5 slides of definitions.
Great, great. Thank you.
Will, are there any other questions? All right, in that case, let's thank Sandra again for.
Thank you.
And I can announce, let's see, we have Jean Bagaria speaking on June 16th, and also, I believe Christopher Turner is going to be speaking on, when is the date for that?
Next week, I believe.
Oh, next week. Okay, so next week we have Christopher Turner. So I'll see you all next week then.
Fine.
Bye.
Thanks, Sandra. Bye.
Yeah, thank you. It was nice seeing you.